Hello and welcome back to ENAE 788M, Hands-on Autonomous Aerial Robotics. So we have talked about the projections and how the camera model works. So now let's move to more 3D version of the computer vision. So let's talk about structure from motion. So in this lecture, we'll cover the first half, which is epipolar geometry. So what is the problem of structure from motion, really? So you have multiple images of the same object from different views, something like this. So you have the same building, you're taking that photos of that building from multiple random different view, and what you want to get is something like this. You want to reconstruct a 3D scene and simultaneously obtain the camera poses of a monocular camera with respect to the given scene. So this procedure is known as structure from motion, or commonly also called as SFM. So as the name suggests, you are creating the entire rigid scene from a set of images with different viewpoints, or equivalently a camera in motion, right? So that's why I call it structure from motion. So a few years ago, Agarwal et al. Published a paper known as Building Rome in a Day, in which they reconstructed the entire city just by using a large collection of photos from the internet. It's implemented in Microsoft Photo Synth software, if you've heard of that. So there are other few open source soft SFM algorithm available online, like there's one called Visual SFM. Just play with them, like download in Windows or something. It's available for Windows and Linux, if I am not wrong. So you can basically input like 50 or 100 of images, some n number of images, and it will create a 3D scene out of it, basically. Just try them. And these are a few samples they created in the paper. So for example, they had Colosseum, Trevi Fountain, Pantheon, and things like that. So they have like 2,000, 3,000 images, and basically they are reconstructed the entire scene. Okay. So moving on. So the yellow dots in this 3D structure you are seeing, in this image you are seeing, is the camera poses from where you clicked each photos. So for example, the thing you're seeing right here is a particular photo that was clicked from some view, right? So this is that view. So you remember feature matching we talked about in the feature lecture, when we talked about panorama stitching and we talked about structure from motion, just the basic idea. So before making the structure or 3D structure, we need to match features. So before talking more about features, let's learn what epipolar geometry is. So it's a field, basically. So let's see what exactly it entails. So let's say you have a point X in the 3D space. Let's say you have a point something. So you have a point X here, right? This is in the 3D world space. Now this X point, just forget about the right side of the image. So let's focus on the left side of the image, right? So these are the two camera centers, C and C dash. So you took an image of this point X or this scene from this view, and you take another one from this view. So you have two image plane. One is this, one is this. So small x and small x dash is the projection of the same world point capital X on the image plane from C and C dash. Okay. So now can you think how to formulate the relationship between the corresponding image points X and X dash? Just think about it. So let C and C dash be respective camera centers, as we discussed, which basically forms the baseline for a stereo system. Okay. Clearly, the points X, X dash, and capital X are collinear. Are coplanar, right? So given that, I can say that my Cx dot Cc dash cross Cx dash must be 0, right? And the plane formed, this plane formed is denoted by pi, and it's called the epipolar plane. Okay. So since these points are coplanar, the rays back projected from x and x dash intersect at x, the capital X, right? This is most significant property in searching for a correspondence. So now let's say that only x is known, not x dash, just the x. Okay. So we know that the point x dash lies in the plane of pi, which is basically governed by the camera baseline CC dash. Hence the point x dash lies on the intersection of line L dash and pi with the second image plane, right? You can see this intersection of this line and this plane. So one more important thing is the line L dash is the image in the second view of the ray back projected from X. So this line L dash is called the epipolar line. You see this line here and you see this line here, right? The line joining, the line which originates from your E and basically intersects this epipolar plane is called the epipolar line. Okay, this is corresponding to the first frame and this is corresponding to the second frame. Okay, and this E dash is basically the baseline of the stereo system. Now the benefit is that you don't need to search for the point corresponding to X in the entire image plane, as it can be restricted to L dash, right? So epipole is the point of intersection of the line joining the camera centers. So this is camera center 1, this is camera center 2. So this is the intersection, the epipolar is the intersection of the line joining the camera centers with the image plane. And epipolar plane, the pi, is the plane containing the baseline. And epipolar line is the intersection of the epipolar plane with the image plane. So L and L dash. So all the epipolar lines intersect at epipole. So now we have a basic of what epipoles and epipolar lines are, like if you have two images from different view of the same scene. So there's a thing called fundamental matrix, which is basically a 3x3 matrix, which relates the corresponding points in two images from different views. Okay, so this F matrix is an algebraic representation of the epipolar geometry as a whole. Okay, so it, as we discussed, it relates the corresponding points in the two images, right, or of the images from two different views of the same scene. Okay, so I can write that my x dash I transpose times F times xi must be 0. So this condition is called epipolar constraint. This is derived from my correspondence condition from epipolar geometry. So my fundamental matrix, as we discussed, is 3x3 matrix, which has 9 unknowns. So I can write that my x dash y dash 1 must be equals to this x dash y dash 1 times my fundamental matrix with 9 unknowns times xi yi 1 must be 0. So if I expand this, I'll get something like this, right? If you want to read about how this is derived, you can just go through this link. I'll just put this link in the description below as well. So this equation for only one common feature, right? Now if I can have multiple features, let's say if I'm doing feature matching, I have like hundreds and thousands of features that are common, right? That's obvious. So these, if I want to write this for m correspondences, I will write something like basically this same matrix n times, right, into whatever my fundamental matrix vector is, right? And this must be 0. So how many points do you think that we need minimum to solve this equation? Just think, like pause the video, think about it, like how many correspondences or what should be the value of m. So remember homography, so where each point correspondence contributes to constraints. So unlike homography, in fundamental matrix estimation, each point only contributes one single constraint as the epipolar constraint. is as the epipolar constraint is say a scalar equation. So thus we require at least 8 points to solve this homogeneous system. So this is why it's called that 8-point algorithm, because we need minimum 8 points to solve this equation. So moving on, you see, if you want to draw these lines, these may or may not intersect. If you basically are trying to draw this epipolar lines, and if you're saying that you want to compute the rank of the fundamental matrix, you might get something like rank is 3, basically a full rank matrix. If you can get that, means these lines may not intersect at the same common point. That means you would have multiple solutions. So if you have n greater than 8, so you have more than 8 correspondences between two images, the fundamental matrix F can be obtained by basically stacking the previous equation in a matrix A, and you can solve Ax equal to 0. So this system of equation can be answered by solving a linear least square. So you can apply SVD, right? But due to noise, you might not get a unique solution from your SVD. So due to some random noise, your matrix F would be of full rank or rank 3. So to enforce it to be of rank 2, the last singular value of your estimated F must be set to 0. So if F is full ranked, you'll get something like this, right? But if F is rank 2 or like one less rank, then it will have if the F is full rank, then it will have an empty null space. That is, it won't have any point that is on the entire set of lines. So there wouldn't be any epipolars basically. So if you can see in the figure, there's for full rank matrix you don't have a common point, and for when the rank of the matrix is 2, you have one common solution, which basically you would need, right? So basically the way you solve it is, as we discussed, you want to solve for x from Ax equal to 0, A being this entire matrix, and basically you write A is equal to U sigma V transpose, and the solution of F is last singular vector of your V, right? And this F computed right now from the solution of this SVD is between the two frames that you took the image from. So let's say you took 3 images, so you will have one fundamental matrix between the image 1 and image 2. You have another fundamental matrix which would be between image 2 and image 3. Basically, you have to recompute fundamental matrix every time, because it depends from where you are taking the image from, right? So let's say this is the feature matching you did from the first let's say this is the feature matching you did from the first 2 scenes. Now the thing is, not all the features are correct, right? You want to remove these features. The way to do is you can use Ransack algorithm, which is based on the estimating of the fundamental matrix. So out of all the possibilities, the F matrix with the maximum number of inliers should be chosen. So let's say for something you have a lot of so if you remove these outliers, basically the red ones are the outliers. Basically, you're removing all the bad F matrix solutions. So the green ones are the ones basically you are having good feature matching by passing through a Ransack from the fundamental matrix. So there's one more important interesting thing that is being roaming around in computer vision field, which is the fundamental matrix song. It was like made by Daniel Wedge. I think probably this is like 15 years old. So he basically wrote a song how to compute fundamental matrix from 2 frames, and he basically derives the equations and how it is. So the link will be in the description below, or if you have the PDF from the link, you can just click this particular link from the PDF. It's a very cool thing if you want to watch. Okay, the next thing is essential matrix. So we have learned about what a fundamental matrix is, right? It's a relationship between the two frames basically for the epipolar. So what we have computed, so since we have computed the F matrix using epipolar constraint, we can find the relative camera poses between two images. So this can be computed using the essential matrix. So essential matrix is another 3x3 matrix, but with some additional properties that relates the corresponding points. And it follows or it obeys the camera pinhole model, unlike your fundamental matrix. So it is important to note that your F is defined in the original image space, which is the pixel coordinate, whereas my essential matrix or E is in the normalized image coordinates. So normalized image coordinates have the origin at the optical center of the image. Also, relative camera poses between two views can be computed using E matrix. Okay, so let's see the thing, right? So it's another 3x3 matrix with additional properties which relates to corresponding points, and it obeys the pinhole model. So you can write the E matrix as my K transpose times F times K transpose. So once you have the K from the previous equations and you know you have a well calibrated camera, you can use this K and you can use the K transpose, and this will give you the essential matrix. So very important thing to note is you took the image of the same scene using the same camera. But if the cameras were different, let's say I took the picture from here from camera 1 and took another picture from here from camera 2. Now what's going to happen is my calibration of or the intrinsics of the two views are different. So now I have to make it K dash rather than just using K, right? So F is, as I said, F is defined in the original image space, which is pixel coordinates, and E is in the normalized image coordinates. Okay, so F had 7 degrees of freedom. That's why we use 8-point algorithm. And E has so think about why F has 7 degrees of freedom. Just pause the video and think about why F has 7 degrees of freedom. So if you remember, F is a 3x3 matrix, which means it has 9 elements. But in F, their ratio is not significant. So if I divide my entire matrix by the last term, which is F33, let's say, everything is going to be scaled, which leaves me with the 8 degrees of freedom. Now, in addition, I have another constraint that my determinant of my fundamental matrix is 0. That's another constraint. That means one more degree of freedom is gone. So that's why F has 7 degrees of freedom. Okay, so just a recap, in my fundamental matrix, I have x dash transpose f x equals 0. In essential matrix, I have y dash transpose into essential into y must be 0 for y and y dash points are corresponding to the same 3D point. And these are again homogeneous normalized image coordinate, not the pixel coordinates from image 1 and 2. Okay, so why are we studying this? So essential matrix basically can be used to estimate the relative pose between two frames. That is, if I take an image from here and another image from here, I can actually tell the relative rotation and translation between these two camera centers. So this can be very useful if you're doing, basically if you're solving structural motion or if you're doing in visual geometry or things like that. So this is a very crucial step. So how do we compute our relative pose using essential matrix? We'll talk about that in the next lecture. That's it for now. Okay, goodbye.